Welcome to the 14th lecture of module 4. In this module, we are discussing reactor design, and we have started with the last couple of lectures we have done. We are working on the temperature and pressure effect. So, before going to this lecture, let us have brief recap on our previous lecture. In the last lecture, we have covered total mass balance in batch reactor, material balance in batch reactor, and then we have done with energy balance in batch reactor. So, although we have done the batch reactor design earlier at the beginning, but here we have considered mainly for energy balance. Then we have seen the temperature and enthalpy relation, how enthalpy and temperature they are related, and we have considered adiabatic operations where we have developed a equation to calculate the adiabatic reaction temperature. So, in this lecture we will start with optimum temperature progression in batch reactor. As we have seen in the last lecture, if we operate the reactor adiabatically, for exothermic reaction, the temperature, adiabatic reaction temperature will change as the reaction proceeds. But if either exothermic or endothermic, the temperature of the system will change, either it decrease or it increase. So, over the reactions it proceeds, the temperature will change in case of the adiabatic reaction. But if we wanted to operate the reactor at a particular temperature, that means we want to operate the reactor in isothermal way, then we will have optimum temperature progression for that, and we will see for exothermic reversible first order reaction with an example how the optimum temperature can be determined. So, optimum temperature progression for a single reaction. If we have single reaction and that is irreversible reaction, the optimum temperature is simply the highest possible temperature, since that will provide the highest possible rate. So, if we have a single reaction either exothermic or endothermic, in both cases as we increase the temperature, the reaction rate will increase and also the conversion will increase because it is irreversible reaction. So, the maximum allowable temperature would be the optimum temperature in case of a single reaction, irreversible reaction, but the maximum allowable temperature will be determined by other factors like how much temperature the reactor can withstand, or at that temperature whether the product degrades. So, we have to run below the temperature product or reactant that degrades at that temperature. So, the maximum allowable temperature will be determined by the property of the reactor stability and the product or reactant stability, and also economics of the system. This temperature so will be determined by boiling of the reactants and operational limits of the reactor. So, you can see the conversion versus temperature plot which is obtained from Levenspiel at different temperature, how the conversion changes or increases, and the maximum allowable temperature where you need to optimize your maximum conversion if you want to get, and if that temperature is allowed with respect to the boiling of the reactants or the operational limits of the reactor, then we can decide that optimum temperature. Another case for an endothermic reaction, but reversible reaction. For this case what will happen, because it is reversible, and endothermic. So, as we increase the temperature, the reaction rate will increase, and because it is endothermic in nature and reversible, so your equilibrium conversion will also increase. So, the best operation is again the highest possible temperature. So, in this case also similar to the single reaction, irreversible reaction, we have seen that the maximum allowable temperature is the optimum temperature. In this case as well, the for endothermic reversible reaction, the base temperature is again the highest possible temperature. Since both the equilibrium conversion and the reaction rate will increase with temperature, so for endothermic reversible reaction, both equilibrium conversion as well as the reaction rate with increase in temperature. So, that is why the maximum allowable temperature would be the optimum temperature for endothermic reversible reaction. Again, in this case the maximum allowable temperature will be determined by the factors which we have discussed, that is the boiling of the reactants or the operational limit of the reactor. The only case where there may be optimum temperature for the single reaction is when we have exothermic reversible reaction. So, if we have exothermic reversible reaction, in that case we have a optimum temperature to operate. For such a reaction, the rate will increase with temperature, but the equilibrium conversion will decrease with increasing temperature. So, we have to optimize the temperature in such a way that we will get maximum conversion with minimum time. So, you can see the maximum allowable temperature over here is the T max, which is shown over here, taken from Levenspiel, and the rate of the reaction, how it is changing, this is the rate path. So, this is at maximum rate path and this line is the equilibrium curve. So, if we can maximize the rate at different temperature, then we can achieve the maximum conversion in minimum time. So, we will go with an example, exothermic first order reversible reaction. So, let us consider this example A to B reversible reaction with rate constant R is equal to K1 Ca minus K minus 1 Cb, which is equal to K1 into Ca minus 1 by capital K Cb. So, this is the forward rate constant is K1, the reverse rate constant is K minus 1 and Ca, Cb, these are the concentration of component A and B. K is the equilibrium constant, capital K is the equilibrium constant. So, this is basically is equal to K1 by K minus 1. If we start with a pure A, that means concentration of A at the beginning is Ca naught. So, from stoichiometry we can write Cb would be equal to Ca naught minus Ca. Now, the forward rate constant and the equilibrium constant we can write in terms of the Arrhenius relation. So, the Arrhenius relation for forward reactions K1 would be equal to A exponential minus Ea by RT, and equilibrium constant capital K is equal to K naught exponential minus delta H by RT. If we substitute K1 and capital K equilibrium constant, this Arrhenius relation in this equation, red equation, we would obtain. So, we have R is equal to K1 into Ca minus 1 by K Cb. So, we will substitute Cb, we know Cb is equal to Ca naught minus Ca. So, if we substitute Cb over here, this would be equal to K1 Ca minus 1 by capital K into Ca naught minus Ca. So, if we multiply, this would be K1 Ca minus 1 by K Ca naught plus 1 by K Ca, and if we rearrange, this would be equal to K1 into 1 plus 1 by K Ca minus K1 by capital K Ca naught. This is Ca. So, this is equal to 1 into 1 plus 1 by K Ca minus K1 by K into Ca naught. Now, if we write R is equal to minus dCA dt, which is equal to K1 into 1 plus 1 by K into Ca minus K1 by K Ca naught. So, from here we can write dCA dt would be equal to minus K1 1 plus 1 by K into Ca plus K1 by K into Ca naught. Now, we have K1 is equal to A exponential minus Ea by RT, and K is equal to K naught exponential minus delta H by RT. So, if we substitute over here, this would be equal to A minus A exponential minus Ea by RT into 1 plus 1 by K naught exponential minus delta H by RT into Ca. So, this is the first part, and second part would be equal to A exponential minus Ea by RT divided by K naught exponential minus delta H by RT into Ca naught. So, this is the concentration versus temperature relation. So, with respect to time. So, from this relation, if we wanted to find a single optimum temperature, if we want to find the optimum single temperature at which to run the reaction, then the temperature is constant with respect to time. So, the earlier equations we have seen that the change in concentration with respect to time, and it has a relation with the temperature. But if we wanted to run the reactor at a single optimum temperature, that means the temperature is constant with respect to time. So, in that case we can integrate the earlier equation, the red equation for concentration of A, to get, say we have Ca by Ca naught is equal to 1 by 1 plus K into 1 plus exponential 1 plus K into exponential minus K1 into 1 plus 1 by K into T. So, we can rearrange that. If we can integrate the earlier equation, we would obtain the concentration profile like this at a constant temperature. So, we can now, since the temperature is constant and we have integrated, we can now substitute K, which is a function of temperature here, and we would obtain 1 by 1 plus K naught exponential minus delta H by RT into 1 plus K naught exponential minus delta H by RT exponential minus A exponential minus EA by RT into 1 plus 1 by K naught exponential minus delta H by RT into T. So, this is the relation if we substitute K and small k1, that is forward rate constant, with a Arrhenius relation, we would obtain the concentration profile like this. Or alternatively, what we can do, we can fix the time required to obtain a particular conversion. So, this relation we can just rearrange to calculate the time required for a particular conversion. So, represented in terms of the concentration. So, if we do that, we would obtain T is equal to 1 by K1 into 1 plus 1 by capital K ln 1 by Ca by Ca naught into 1 plus 1 by capital K minus 1 by K. Now, if we substitute K and K1, we would have 1 by A exponential minus EA by RT into 1 plus 1 by K naught exponential minus delta H by RT ln 1 by Ca by Ca naught into 1 plus 1 by K naught exponential minus EA minus delta H by RT minus 1 by K naught into exponential minus delta H by RT. So, this we would obtain if we want to get a time required for a particular conversion. Now, to find the optimum isothermal operation, we either want to minimize Ca for a fixed reaction time, or we want to minimize the reaction time for a fixed outlet concentration. So, either of these two we need to consider. So, either minimize Ca for a fixed reaction time or minimize reaction time for a fixed outlet concentration. These two things we can do. So, in each case what we need to do, we take the partial derivative of the quantity we want to minimize with respect to temperature and holding the other quantity constant. That means, if we wanted to minimize the concentration, we will take partial derivative of concentration with respect to temperature, keeping the time constant, or in other case we can take partial derivative of time with respect to temperature, keeping the outlet concentration constant, and then we need to set it equal to 0 and solve for the temperature. And analytical solutions for the optimum temperature can readily be obtained, but it is fairly long and messy. So, one can use the software available, like if we can use Mathematica, Maple or MATLAB, this solution is very easy to solve and very straightforward. Now, instead of finding a fixed optimum temperature, that is at one temperature to run the reactions, reversible exothermic reaction, that is sometimes not possible to obtain the highest conversion in minimum time. So, it is better to use the arbitrary temperature control. We can control arbitrarily the temperature and we may select optimum temperature trajectories rather than a single temperature. Optimum temperature trajectories means we are not considering a single optimum temperature to run the reactor. The temperature will gradually change depending on our requirement to optimize the conversion and the reaction time. So, intuitively it makes sense that for a reversible exothermic reaction, what we wanted to do initially, we need to have relatively high temperature because the conversion is low. So, we can very quickly achieve a good conversion with a minimum time. So, if we have high temperature, the reaction rate would be faster and it will give the conversion higher in a smaller time. As the conversion increases, at higher conversion, we would want to decrease the temperature to avoid the equilibrium relations. Since it is exothermic reversible reaction, as the conversion will increase, it will be limited by the equilibrium relations. That we can avoid if we decrease the temperature at higher conversion. In that case, we will optimize the temperature trajectories depending on our requirements. So, it can be shown for a single reaction, the maximum conversion in minimum time can be achieved simply by maximizing the rate at each point of time. This seems obvious, but in case of multiple reactions, it is no longer necessarily true. So, this will be done for a single reversible reaction. We can maximize the rate at a different point of time and we can achieve maximum conversion with minimum time, but for multiple reactions this may not be necessarily valid. Now, if we consider single reversible exothermic reaction and rate, we know R is equal to K1 Ca minus 1 by capital K Cb, which is equal to A exponential minus Ea by RT into Ca minus A by capital K naught exponential minus E A minus delta H by R T C B. So, if we substitute K 1 and K with the Arrhenius relation, and then if we rearrange this relation, we would obtain this expression. Now, if we take partial derivative with respect to T at a fixed concentration. So, taking partial derivative with respect to temperature at fixed concentration. So, you would obtain del R del T would be equal to A, which is equal to A E A divided by R T square exponential minus E A by R T into C A minus A into E A minus delta H divided by K naught R T square into exponential minus E A minus delta H divided by R T into C B. So, this is the partial derivative of rate with respect to temperature at a fixed concentration. Now, if we set this equal to 0, so we would obtain setting del R del T equal to 0 and multiplying both sides by R T square by A. So, you would obtain E A exponential minus E A by R T into C A is equal to E A minus delta H by K naught into exponential minus E A minus delta H by R T into C B. So, here as we are optimizing the rate, so the temperature which we obtain is the optimum temperature. So, we can write R T optimum E A minus delta H by K naught E A into C B by C A is equal to exponential minus delta H by R T, or we can write T optimum would be equal to minus delta H, this is R T optimum. So, T optimum we can write minus delta H divided by R ln E A minus delta H by K naught E A into C B by C A. So, this temperature T optimum minus delta H by R ln E A minus delta H by RT by K naught E naught into Cb by Ca. So, this gives the optimum temperature trajectories in terms of the concentration or the extent of reaction when the reaction progress. Initially, for an exothermic reaction, if we consider exothermic reaction, then delta H is negative, and so this will give an optimum temperature that is negative, not a physically meaningful or significant results. That means Cb at the beginning is 0, and so this term is negative ln term in the denominator. So, at the beginning the upper term is positive because delta H is negative. So, the numerator over here at the start of the reaction, this is T optimum is negative. So, which is not physically meaningful. So, the optimum temperature becomes infinite when the quantity inside the logarithm in the denominator is equal to 1. So, as the reaction progressed, the conversion changes, the term over here in the denominator under ln terms, this becomes 1, then it indicates the optimum temperature is infinite. That means, here Cb by Ca naught is equal to K naught into Ea divided by Ea minus delta H. So, this is the limits where the temperature becomes infinite. That means, for conversion smaller than the critical values, that means Cb by Ca is equal to K naught Ea by Ea minus delta H. For conversion smaller than this critical value, the optimum temperature is as high as possible. So, if we can initially, if we would like to get a higher reaction rate up to this critical conversion, when the Cb by Ca would be equal to this term where the ln term will be infinite. So, then we can keep the temperature as high as possible to reach the higher conversion with a minimum time. Then as the reaction proceeds past this point, the optimum temperature will decrease. So, we have to, because it is exothermic reaction, and we have to lower down the temperature. So, the optimum temperature trajectories for a batch reactor with a single reversible reaction to run the reactor at highest possible temperature, that is T max, until the conversion reaches a point where the optimum temperature obtained from the equation above is T max. So, here till it reaches the critical conversion values, we have to keep the temperature as high as possible, and that is determined by the reactor operational limits and the boiling of the reactants. Those parameters will decide at the beginning what temperature we should maintain at this case till the smaller than the critical value, and after that point the optimum temperature can be obtained from the equation given above. So, then we can obtain the T optimum relations. From there, what is the optimum temperature we need to maintain, that we can obtain from the relation. Now, one can predict how the temperature should vary in time by integrating the equation of concentration with with rate evaluated at optimum temperature. That means, we know dCA dt is equal to A exponential minus EA by RT into 1 plus 1 by K naught exponential minus delta H by RT into CA minus plus A into exponential minus EA by RT divided by K naught exponential minus delta H by RT into CA naught. If we set with T is equal to optimum temperature, so after critical conversion we can write dCA by dt, dCA by dt would be equal to A into EA by minus delta H by K naught E naught into CA naught minus CA by CA to the power EA by delta H into 1 plus EA CA divided by EA minus delta H into CA naught minus CA whole into CA minus A by K naught EA minus delta H by K naught EA into CA naught minus CA divided by CA to the power EA minus delta H by delta H into CA naught. So, this is the relation if we consider T as the optimum temperature, and then we can substitute T optimum over here in this relation. So, dCA dt we would obtain like this. So, this can be integrated to give the concentration as a function of time, and the equation used to obtain the optimum temperature then gives the temperature as a function of time. So, the earlier equations which we obtained, that is dCA dt, which is a function of conversion or concentration. So, that this we can integrate, the earlier equations which we have developed can be integrated to give the concentration profile, that is concentration versus time, and then equation used to obtain the optimum temperature then gives the temperature as a function of time. So, that means this concentration versus time we need to incorporate into the relation, that is T optimum is equal to minus delta H by R ln minus EA minus delta H by K naught EA into CB by CA. So, the concentration profile if we substitute over here in this optimum temperature, then we will get the temperature, optimum temperature versus the time. Now, finally, this temperature and concentration can be used in the enthalpy balance equation to obtain the heat removal rate required as a function of time to maintain the optimum temperature. So, we have temperature as a function of time and concentration as a function of time. So, both we can use in case of the energy balance equation, which will give the heat removal rate required as a function of time. So, that will tell about the how to maintain the optimum temperature. So, this is how we can do it, but since the calculation is analytical calculation is really lengthy. So, we can use the software like Mathematica or Maple to solve these equations. Now, let us take an example of methanol production from synthesis gas. So, basically the reaction is exothermic in nature. So, like CO plus twice hydrogen reversibly reacting producing methanol. You could see here in this plot the reaction rate is plotted versus temperature and extent of reactions. So, we call it contour plot, and in this case you could see that there are three different lines over here. The dark line over here, the thicker dark line at the middle, this one, this is basically the equilibrium line. So, the dark line shows the equilibrium conditions where the reaction rate is 0. So, at this point the reaction rate is 0. This line, the dark line, which is thinner dark line, represents how the rate of reaction progress with the extent of reaction and the temperature. The white line over here, you could see the white line, this is the maximum rate trajectory. So, it represents maximum rate line. The white line gives the optimal trajectory. It is the temperature that gives the maximum rate for any given extent of reactions. So, at a particular extent of reactions over here, this gives the maximum rate at that temperature. To get the maximum amount of reaction in a minimum time, we would follow this white curve. So, if we wanted to have maximum amount of reactions to be happen with a minimum time, we need to follow this white line. So, we could notice that it goes off towards very high temperature at low extent of reactions. If we consider low extent of reactions, so very less here, say close to that, the maximum rate you could see it is going off. At low conversion, the maximum rate goes off at very high temperature. So, what is our target? Say initially our temperature would be fixed by some other considerations, and that would be the maximum temperature we need to fix. Suppose the maximum allowable temperature for this reaction is 500 degree centigrade. So, say 500 Kelvin. So, maximum allowable temperature for this reaction, if we consider say 500 Kelvin. Now, at 500 Kelvin, say over here, so we should run the reactions at start with at high temperature, and reaction will proceed through this and it will reach like this. So, the conversion we will obtain here is about this. Now, if we keep on doing the experiment, running the experiments further at this temperature, the equilibrium conversion will decrease, the rate will decrease as well as the conversion will decrease, because it will reach to the equilibrium. So, then we want to keep the reactor at 500 Kelvin up to an extent of reaction, say about 0.5 or so. So, this is basically, this means that this is the temperature close to we cannot keep up to 500. So, we may keep the temperature up to this. So, the conversion is about 0.3 and then reduce the temperature to follow the white line. So, we need to reduce the temperature say about 450 and then we can run for a certain period of time to reach the conversion over here. And again we reduce the temperature say around 400 or so, and so it will reach this conversion. So, we have to optimize the temperature step by step or reduce the temperature, so that we can achieve the maximum conversion possible with a minimum time. So, this is how the batch reactor operation we can do with a minimum time and how the temperature would progress. So, thank you very much for attending this lecture, and we will continue our discussion on the energy balance and optimum temperature progression for other two idealized reactors, that is plug flow reactor and the continuous stir tank reactor, in our subsequent lectures. Thank you.